So this video looks at cardiac dynamics, part of the cardiovascular system, the anatomy and physiology in ASPE. And very much is based around this equation, Q equals HR times SV, which we'll look at each component as we go through. So the specification asks you to be able to describe the relationship between three things: stroke volume, heart rate, and cardiac output. And you need to know these in terms of resting values and the units for each of those components, but also what happens when we exercise and exercise at different intensities. So you need to be able to relate those values to different, typically submaximal or maximal activities. And as we just said, a lot of the sports that you guys will take part in will involve either a mixture, or it will be submaximal or maximal activities. But typically a lot of the games we play involve us and our bodies being able to function in both of these ways. So the equation then, let's start off looking at the Q part of it. So we're going to look at this, which is cardiac output. And basically what this means is, you can translate the name really, the output of the heart. So cardiac tends to refer to heart, and we're looking at how much blood, the volume of blood, is ejected from the ventricles per minute. And it's important that it's per minute, to not be confused with one of the others. So the volume of blood ejected from the ventricles per minute. The unit is litres per minute. And you need to appreciate that your body will adjust to the demand you put on it instantaneously almost, and almost in anticipation of things. So your body can change the value of cardiac output based on what you're doing, whether you're walking or jogging or sprinting. So here's a graph to show you hopefully what happens to your cardiac output values in litres per minute during both submaximal and maximal. Submaximal's in red and maximal's in blue. So let's have a look. At rest, we circulate about 5 litres per minute. So we've got this resting level here before we've exercised. Now what you'll see also is a gradual increase before we've started exercise. And quite often we anticipate exercise and our body responds physiologically, and we start circulating more blood to prepare us for our exercise. We have then quite a steep or rapid increase in cardiac output. And during submaximal exercise, we then plateau. This flat line, level line here is what we call plateau. And the value that we are circulating around our body, the blood, is increased from rest, but stays about the same during submaximal exercise. At the end of the exercise, we have a rapid decrease, and then a more gradual decrease until we get back to normal levels. So that's submaximal exercise. Maximal exercise, the same start, the same anticipatory rise, and the rapid increase is there, but instead of plateauing, there's then a gradual increase until we reach maximal levels. So again, it's much higher. Could be about 20 to 40 litres per minute circulating around your body from your ventricles. After exercise, there's a dramatic drop, and again, then a gradual decrease before we stop and we have fully recovered. So now let's look at heart rate. Heart rate, you should know, is beats of the heart per minute, and the units is beats per minute, BPM. Basically, this is how many times does your heart go through the cardiac cycle, how many times does it contract and then relax in 1 minute. Now, some other little bits of information about heart rate. You should be able to calculate your maximum heart rate. You do that by taking 220 and subtracting your age from it. So many of you will be doing 220 minus 17, so your maximum heart rate is 203. If you were age 35, it would be 220 minus 35, and you have a maximum heart rate of 185. These values are not absolute. They can be variable, but they're a very broad guideline. Just to say, actually, obviously, as you get older, your maximum heart rate decreases. Resting heart rate is another term you should know. So an average adult heart rate is 72 beats per minute. If you're a trained athlete, typically yours might be lower, and if your resting heart rate is lower, it is often assumed as an indicator that you are cardiovascularly fit. So if your heart rate is 60 or 55, I know some endurance athletes, international elite athletes, might have one as low as 35 or 40, then it indicates that your heart is stronger and bigger and can eject more and has to beat less. Now, resting heart rate is important for fitness, but also in terms of this heart rate range. You calculate heart rate range by knowing your maximum heart rate and subtracting your resting heart rate. So here's resting heart rate down the bottom, maximum heart rate up the top, and the difference between those two values is your heart rate range indicated by the arrow there. So here's a couple of examples. They're both age 17, and their maximum heart rate therefore is 203. So 203 is this. One athlete, however, has a resting heart rate of 60, and the difference between those two values is 143. So from rest, they could increase their heart rate 143 beats. The other person is less fit and has a resting heart rate of 75, which means their heart rate range is 128. So they have less potential to increase and potential to improve or enhance or put more demand on their cardiovascular system. So this person here with the greater heart rate range, the lower resting heart rate, probably would do better at aerobic events. Here's a graph really just to illustrate that we have an important relationship between heart rate and work intensity, and it is called a linear relationship, i.e. when you work harder, your heart rate goes up proportionally. So there's a relationship between work intensity and heart rate. So heart rate, here's a look at the graph for the submaximal and the maximal values, beats per minute. Rest is about anywhere but 60 to 72 is kind of average. We've got that anticipatory rise. We've then got a rapid increase, and submaximal exercise brings a plateau. We call this steady state. That might be at maybe 120, 150 beats per minute. After exercise, there's a rapid decrease, and you return gradually until you're down to normal levels. That's submaximal exercise. Maximally then has the same pattern, dramatic rapid increase, and then a gradual increase until you get your maximal heart rate, which might be 180 depending on if you're 40, it would be 180. Depending on your age, that could be a different value. After exercise, rapid decrease, and then a gradual decrease until you're back down to resting levels. Here's the same sort of graph, but I've got some letters identified here, and I've been using specific language when I've been talking about the pattern here. So let's just have a look at those. So here's our graph. A is where there's an increase in heart rate and cardiac output before you even start exercising, and that's due to anticipation, where adrenaline is released from your adrenal glands, and that increases your heart rate before you even start moving. B, in both cases then we have a rapid increase, a dramatic increase in heart rate and in cardiac output. At this point we're trying to work aerobically, but we're needing help from our anaerobic system. C, so we're looking at the maximal exercise now, is where we continue to increase our heart rate, but it's more gradual until we get up to our maximum. D would have been, for the submaximal, the plateau, the levelling off, and we call this steady state, where we've got a match between the oxygen we're circulating and the demand for oxygen, so we've got what we need. After exercise then, in both cases, E involves a rapid decrease in heart rate or cardiac output, and F is then the gradual return back down to resting levels. And this increased heart rate and cardiac output help us replenish all our system with oxygen and remove all our waste products. Here's just another graph. You can pause and have a look at this. So we've got heart rate, we've got oxygen uptake, how much oxygen our muscles use, and workload and time. And basically, as time goes by and we're working harder, we can see that both heart rate and oxygen uptake increase and both decrease in recovery. So they follow the same pattern. Some important terms in terms of heart rate. Bradycardia. So if you train really, really hard, your heart can become stronger, the muscular walls become thicker. That's called cardiac hypertrophy, so the thickening of the muscular walls, the myocardium. Now if you have a stronger heart contraction, your heart probably won't need to beat as many times and your heart rate is lower. So if your heart rate is below 60 beats per minute, it is bradycardic, or there is bradycardia. If your heart rate is elevated and goes above 100 beats per minute, it's tachycardic, and that is tachycardia. So just some terms you might appreciate. Lastly then, let's look at stroke volume. So stroke volume is the volume of blood ejected from the ventricles per heartbeat, not per minute, per heartbeat. So every time your heart contracts, this is the amount of blood it ejects and squeezes out. And the unit is milliliters. Now, importantly, stroke volume can increase when you're exercising and working harder, but it does reach a point where it plateaus. It can't eject any more than it does. And we'll look at that in the graph. So here's our graph, stroke volume in milliliters. Resting levels are about 70 milliliters. We've got our anticipatory rise, so it increases. We've got a more dramatic increase. And then we've got this plateauing, this leveling off, where we've reached our maximum stroke volume value. And this typically happens at about 40 to 60% of our max heart rate. So our heart rate can still go on beyond this level of intensity, but our stroke volume is limited there. And then of course as exercise goes on, sometimes it can decrease in its value. Basically your heart is beating way too fast to allow your heart to fill, and therefore it can't eject as much blood each time. Here's another graph, same sort of thing, just showing the plateau at around 40 to 60% of your maximum heart rate. And again, sometimes the value of stroke volume can drop a little bit after a period of time. So stroke volume is really important, and it's dependent on your ability of your heart to fill and the ability of your heart to send out that blood.